So first of all, good evening, everyone. So today we are going to discuss a introduction. Okay, just a introduction session on the course. Okay, so what we are going to develop in these 3 months course. I think I already shared the course content, the curriculum for everyone, right? So today we will discuss deep into like what exactly you are going to learn and what you will get from these 3 months course and what you are developing one by one stepwise. Okay, so in each week what we are going to learn and what assignments we are doing, and what type of project, finally what is the output. Okay, from the course. So those things we are going to discuss today. So whatever the doubts you have, okay, if you have any doubts and all, you can clear in the session itself. Okay, so the course is like a developing of RISC-V 32-bit processor. Okay, so actually here system on chip, in the sense system on chip is different. Developing of RISC-V processor is different. Okay, but system on chip is also important thing for the verification engineer. Okay, so whatever we are working in the real time, we need to
Yeah.
understand in a SOC level, right? So that's why we have included the SOC concepts. Okay, the major SOC concepts which industries prefer. Okay, from each every candidate. So those concepts we have included. With that, RISC-V development. RISC-V is already, it's an open source. Okay, it is available in the internet and all, but everyone won't understand the architecture and how we need to develop everything. Like a RISC-V is a complex thing. Okay, very complex thing. It is not like a basic architecture and all. So as a student level, or if you are even working, you may not understand whole process. Like it have different stages, 5 stages it would have. So 5 stage pipelining. So there would be different types of instructions. So how we can develop a RTL coding for a RISC-V architecture. So everyone won't able to understand their self, right? So that's why for easy understanding purpose and how we can develop our own project, mainly for hands-on experience. Okay, so everywhere the industry choose who will write the logical coding very easily. Okay, nowadays even if we Google anything, we are getting the code and all, or even chat gpt, from chat gpt like that there are some AI tools out there. From there also we are getting different coding. Even just if you put some prompt, we are getting the data, everything, right? but but how we can implement, how can we develop our own project, how we can get hands-on experience by debugging different type of errors. Okay, so whenever we are doing our own, like then only we are able to solve some errors. From that we will get the experience, right? So for, that is the main intention of this project. Okay, so coming to the course curriculum. So this is a 3 months duration course. Okay. So in these 3 months, first of all, we are starting with the basic SOC level concepts. Okay. So what is mean by ASIC, FPGA chips? I think you already may know. There are some undergraduate students also in this batch. So we need to cover from basic things, right? So what is the difference between ASIC and FPGA chips? And SOC architecture and each block in detailed explanation, and what are the different blocks involving in the SOC. Okay, SOC means it's a very big architecture, the complex architecture. So we need to understand every path. Like there will be some control path, data path will be there, different type of signals will be there, and they will be connected with some peripherals. Okay, some IO devices would be connected, and different types of processors would be connected, like a CPU or graphic processing unit, and some digital signal processors will be there. So, and there will be different type of IPs. So we need to understand the overall SOC architecture. What is the difference between SOC and IP level verification? So then we are discussing briefly about the functionality of each block. Okay, so every block have different functionality, right? So exactly how the industry's SOCs will be there. If you Google any SOC, we will get the basic architecture of SOC, like which contains a GPU or CPU, some memory unit, and some DSP signals and some IO peripherals. Only these things would be get, right? But what exactly the industry's SOC will involve? Okay, those different blocks we are going to discuss here. And what are the different teams will be involved in the SOC verification? So there will be thousands, lakhs of engineers involvement will be there, right? For every flow, okay, in every step, if you see. So what are the different teams involvement and compared to the traditional integrated circuit, what we have seen in olden days, what is the difference between traditional IC integrated circuit and SOC? And what is the verification flow of a SOC? Okay, so whenever we are developing, as we are a verification engineer, so when you are writing some test cases, so how the test case is going to be executed in a SOC level? Okay, and then IP verification, the difference between IP, subsystem, and SOC verification, we are going to discuss very briefly. And then the overview of SOC level verification involved in the processor verification. Okay, so like what are the steps we need to follow? If you consider any block in the pre-silicon verification and in the post-silicon verification, what are the different things involved in the processor verification? So overall, you will get the idea about the verification in first 14 days. Okay, there will be weekly 6 hours, right? So weekly three days sessions will be there, 3 days or 2 days sessions will be there. So based on that, you're going to learn these things for first 14 days or 15 days. Okay. So, and then from here, we are going to start our main course. Okay. Main course in the sense a RISC-V processor, right? So, first of all, we are going to discuss what is the history of RISC-V processor. Okay. Processor in the sense we already know, where we create, like if you want to create any hardware, okay, then it need different types of IPs or different types of functional blocks are required. So every hardware, every system, if you consider, there would be some hardware and the software. So what are the different type of hardware modules and what are the different types of software modules and how this processor has evolved? Okay, so compared to the Intel x86 processor, and we have from AMD, we have CISC processor. So what is the difference between CISC processor and RISC-V processor and how it was developed from von Neumann architecture? So all the basic things, the evolvement we are going to discuss. Okay. And then the overview of the instruction set architecture. So one of the main thing, processor is nothing but it execute number of instructions, right? So how the instruction architecture has defined in the RISC-V processor? Like there are different types of instructions. Can anyone tell me what are the different type of instruction set is there in RISC-V processor?
R type, I type, S type, B type, J type.
So there
Arithmetic
are
in
yeah, then
arithmetic instructions, branch instructions, looping instructions, like this.
yeah, there will be like immediate data instruction, load and store instructions and branch type instructions, jump instructions. There are different types of instructions. Okay, so we are going to see in depth of every instruction. Suppose if any expression has given, like you want to do some arithmetic and logical operation, like a plus b into c is greater than or equal to some x. So those type of logical expression, how you will implement using the assembly language programming. Okay, So based on the instruction set, we are going to see some assembly language programming. Okay. And then RISC-V pipeline architecture. So in this processor, main thing is the pipeline architecture. So there would be 5 stages of pipeline. So how we are going to implement each stage, okay, in a RTL, and also deep into the each stage of the pipeline. Okay, deep into the sense, suppose there is a program counter. Okay, how the program counter would be designed, and what are the different signals for the program counter. Okay, and there is a decoder. What would be the different signals, and what is the internal logic of the decoder. Okay, and execution stage, the internal logic of the execution stage. Okay, so all the like a pipeline architecture we are going to discuss, and the detailed explanation of instruction types, whatever I told before. There would be a different format for each instruction, right? Suppose if you take a immediate instruction, there will be source registers and destination register, and sometimes if you are writing a complex expressions, there will be some temporary registers also, right? So how we are going to write a assembly program, so those things we are going to discuss. And here, whatever I mentioned, R type, I type, S type, B type, J type. So everything in detailly we are going to discuss. Another main thing is the detailed explanation of data hazards, control hazards of RISC-V pipeline. Okay. So whenever we are using this 5-stage pipeline, there would be some limitations. There will be some occurrence of data hazards and control hazards. Okay, so we are going to discuss in depth of in that what is mean by stall. Okay, so in control hazards, what are the different hazards are involved, the classification. So everything we are going to discuss with an example. Okay, so main intention of this project is how we will develop our own project by our own. You should be in a stage of developing at least a block. Okay, we cannot develop a overall project by one person. If you go for industry also, we cannot develop a overall project by one person. At least one block, how you will develop by your own. Okay, so you are going to form a group. Okay, 10 members, or if there are 20 members, so there would be 2 groups or 3 groups. So we need to share our work in the group. Okay, and we need to develop from scratch. Okay, if you are not able to develop, then we will help you with the RTL code. Okay, finally we will provide the RTL code, that is secondary. But mostly we need to try how we can write the program by our own. At least a simple logics. Okay, suppose decoder is there, how we can develop a simple decoder logic. Like that program counter, how we can write a simple program counter like that. Okay, and hands-on practice for assembly language programming. So for each type of instruction, we will provide the assignments, and also we are going to do some assembly language programming in the session. Okay, and then RISC-V execution stages and the pipeline. So in the execution stages, so different blocks if you go for micro architecture, different blocks will be involved, right? So how we are going to write a program for different those all in micro architecture level. So that thing we are going to see. And ALU data path for R type, I type, S type, B type, and the J type. So we are going to generate the ALU data path and the control path for all instructions, because here instruction means we are simply telling it's a I type, immediate type. Or if you're seeing a B type means branch type. But how exactly that branch type is going to implement in a micro architecture level? In the branch type, there would be some conditions, if else conditions, right? So if condition is satisfied, that particular statement would be executed. Else the condition satisfied, that particular statement would be executed. So how you are going to put that branch type instruction into the like hardware level in the sense in a ALU data path level. Okay, so for every instructions we are going to design the hardware, the micro architecture, And then finally, by using all these micro architectures, we are going to develop a RTL design using the Verilog HDL. Okay. So then we are going to see the verification part in SV or UVM. Okay. So you may have some doubt why we are writing the HDL language. Here instructions would be performed like in assembly language programming, like in a processor, right? So here what we are going to do means first if you see the any logical expression, suppose any type of instruction, the RISC-V would use internal structure. If you see how the application level language to the machine language, so the instruction would be compiled by the RISC-V processor. So after compilation, the expression would be converted into the instruction set. Suppose I will write a expression. Suppose x is equal to y plus 5 into or some into z, and it should be greater than 5 or something. We are checking this expression. Okay, so this is what the expression. The expression would be converted into the instruction set. Okay, based on the I type or branch type, whatever. After we are compiling this expression, after compiling the data, it would be converted into the instruction set, and then from the instruction after assembler, okay, after assembler, after RISC-V assembler, it would be converted into the machine program. Okay, so the table, we will have one table format, right? So what is mean by a instruction format? For every format, suppose if you take a I type or J type, whatever, it have some format. Okay, so what is the source register and what is the destination register, and it have some opcode and offset addresses. Based on that, it would convert into the binary value. That binary value would be understood by the RISC-V processor. So this is what happening. Okay, right? So for every stage, I will show you more clearly. So if you observe here, suppose just a second. Okay, so if you observe here, the internal architecture of RISC-V, so it have the program counter. Okay, first of all, we use the program counter, which is a byte addressing in the RISC-V processor. From the program counter, we will get the instructions. That is the first stage. So in RISC-V, we have total 5 stages: fetching stage, decoding stage, execution stage, memory stage, write back stage. Okay, so this is the internal architecture of the RISC-V, normal top level architecture. But if you go for micro level, in micro level, we'll have different, some other blocks internally. Okay, so here, first stage is the program counter. So we are going to design the program counter here, which is a byte addressing, and the instruction memory. From the program counter will get the instructions. So we need to design the instruction memory separately, and then we are giving that instruction data to the decode stage. In the decode stage, how the internal logic see. normally we have one decode block, right? So if you go from internal microarchitecture, this is the decode stage. Okay. So from the decode stage, after decoding that particular instruction, okay, decoding in the sense you are writing some A plus B. That A plus B will be converted into that particular instruction and then sent to the execution stage. Okay, in the execution stage, there will be a ALU, okay, to perform the arithmetic and logical operation. From the ALU, there would be a memory stage. In the memory stage, the data would be written to the memory or to the register. Okay, so this is the internal architecture of the five-stage pipelining. Okay, so how we are going to design this five-stage pipelining using Verilog HDL? Suppose this is the instruction memory block, first one. So this instruction memory block, we are going to write the Verilog programming. Okay, so the first we get the data from the program counter. There would be internal architecture for the instruction memory block. So based on that internal architecture, we are going to implement the Verilog design. Okay, so in the whenever we are coming to this stage, I will assign each block to each group. Okay, like 2 members or 3 members, I will assign particular block. So you can take some time and you can develop. Okay, if you are not able to develop, I will provide the design code. Okay, so here we are going to develop the instruction block, like the data memory block and some general purpose register block. Okay, because from that register only we are going to send the data, right? So instruction and the data, and then instruction fetch stage. So here in this block, we are going to fetch the instruction. So that is a separate HDL block. And then the decode stage module. So here the decode stage module, we are going to implement separately. And then execution stage module, these are just top level. Okay, I'm just showing how we are going to develop each program. But before, if you need to develop these things, means first of all we need to understand the instruction set. We need to understand clearly on the pipeline architecture, okay, and the micro architecture of the pipeline. And then we able to design, we able to write the Verilog HDL program for each stage, right? So then execution stage and memory access stage, we are developing the program, and the write back stage. Okay, so at finally we are going to design a RISC-V five-stage pipeline in this manner. Okay, from RTL, from basic micro architecture to the RTL schematic. Okay, so this is the plan for this 3 months duration. Okay, up to RISC-V processor. So this is what we are going to generate. Okay, everyone understood up to here? Do you have any doubts? Is there any doubts, everyone?
No, man.
Okay.
No, Prashanti.
Yeah. So here mainly you need, if you want to develop these things, first of all we mainly need to concentrate on the instruction set architecture for each instruction, and then pipeline architecture. Okay, the micro architecture level, and then data part, control part. And also always we need to look into low power analysis. Okay, power conditions also will be there, power constraints. So how we will write with a low power analysis with those concepts we use here. Okay, so how we can reduce the power whenever it meeting to the whenever the clock is triggering at high power. Okay, we always need to check that power analysis here. And then we after this RISC-V development, we are moving to the SOC level verification, third module. Okay, so here why we are moving again SOC verification? Here we need to know some of the things. Basically, I can cover these things at starting only, but RISC-V is the main thing, right? So after that, we will cover these things. Okay, like pre-silicon, post-silicon verification at SOC level. So why we are moving to the pre-silicon, why we are not able to capture all the bugs in the pre-silicon, okay, and then why we are moving to post-silicon at S4C level, and what are the different teams involved in the pre-silicon and post-silicon, and what is the main difference between DFT and DFT, and how we can develop a test plan. These all things mostly when we are designing for the RISC-V processor, there only you will get, okay, because there we design the test plan for RISC-V, okay, and we will create some test cases, okay. So based on the test cases, we will verify each functionality for RISC-V processor. There only you will get those things. And separately, we are going to see in a S4C level how we can avoid the errors and what are the main important steps for the regression, why we are doing the regression, okay, if any how we can check either test pass fail or error signature, and test ID, test location. So how we can check all these things, we are discussing separately. But mostly when we are designing a RISC-V, there only you will get, because everything we are using in UVM, right? So how we solve the UVM errors, okay, so everything from that only you will get, okay. So another thing is so after executing that 5-stage pipeline, if you go in detail, so this is how we are going to develop the RISC-V 32i. This is the top module. In this top module, we are divided into the stages, okay, the stage 1. So how what are the things involved in the stage 1? So we are going to observe the waveforms and all, the output, and the stage 2. So I'm not going any internal architecture now, because even if I explain internal architecture and all in the first session, you won't understand. So I'm just want to create some enthusiastic, like what you are going to develop. So you must have some idea, right? So what you are going to learn in these 3 months. So for that purpose, I'm just taking this session. Okay, so like this in stages wise. So as we are seeing like a 5-stage pipeline, in each stage, how we are developing some code. Okay, so that's what the intention here. Another thing is here, suppose if you see in SOC level architecture, okay, in a system on chip, there will be several blocks. So there will be like different IPs, different subsystems will be there, like AXI bus. The AXI bus is used to connect different blocks, right? So if you observe, we are concentrating in this course on only this RISC-V processor implementation, only RISC-V processor implementation, right? So if we go some extent, if we go beyond that, okay, so what we can do, like why can't we integrate that RISC-V processor with a memory controller, with the main memory? Okay, so this is extra we have added to this project. Actually, we didn't mention this thing with the in the course curriculum, but here we are going to develop, we are going to design, okay, a RISC-V project, RISC-V processor core integrating with a memory or some controller or some DMA controller. Okay, finally we are going to see this thing, a IP, separate IP integrating with another core IP. This is the main intention of the project. Okay, everyone understood? I think I'm a bit fast, right?
Yeah, got the rough idea at least. Not understood, but yeah.
Okay, okay. Yeah, I didn't explain everything in detail. I just given the overview. So first, what you're going to learn, like a basic concepts of S4C or S4C level verification, and then in RISC-V processor, what we are going to implement. After implementing a RISC-V processor, how we are integrating with the separate IP, like not only memory. If you want to integrate with some video processor, like any some DSP processor, or at least some UART. Okay, so UART is a peripheral here, right? Like that AXI peripheral, if you want to implement, you can you can select any of the IP. Okay. So so if you want to implement in this way means we must have very clear idea on very like hands-on practice on instruction set architecture and the pipeline implementation. Already I think you know the Verilog HDL, right? Okay, can you join for the next
Yes.
session, everyone, with the same link? The session duration is ended. Can you join again?
Yeah, sure.
Okay, so if you have any doubts, you can ask now. Okay, so from this week only, we are going to start the syllabus, this course. Okay, so first we will start with the SOC concepts and then we'll start with the RISC-V processor. Okay, so there would be mostly I will take the sessions on weekends. Okay, Saturday, Sunday, and one weekday session. And for every session, there will be the assignments. So suppose this RISC-V processor is there. So I will provide the assignments for each session. So you need to submit the assignments. And finally, we will develop combinedly, we will try to develop the program. So if you are not able to try develop that, I will share you the RTL design. Okay. So this is the main intention of this course. And here we are going to use the Xilinx Vivado tool. Okay, so here mainly we are concentrating on like how to design a test bench, how to generate, how we can write a logical coding. In my intention, for verification engineer, any tool is okay because the tool is just do the verification. I mean, it just do the simulation and it will produce the output, right? So as a verification engineer, main thing is we need to write the program, we need to develop some test cases, some test plan, we need to reach the functionality and we need to reach 100% coverage, right? So those things, if you write in any tool, will get same output, right? So that's why, in my opinion, every tool is same. But if you want if you take some cadence or synopsis, just some options will be more, some features will be more. Other than that, in every tool, we'll check the verification. Whatever we are writing the test case, we'll do the simulation and we'll check the output. Okay. But if you go for physical design, that would be different. Nowadays, physical design means everything coming in a tool only because everything is automated, right? So manually we cannot do anything. So automated in the sense every small thing we are generating from the tool. So for physical design, tools are mandatory. Okay, license version we need to go. But for verification engineer, any tool would be enough. Mainly, we need to concentrate on writing the test cases. Okay, debugging. Main thing is how we can debug a code. So that is the main thing. So by end of this course, everyone will have that hands-on experience for sure. Okay, this time we have highly concentrated on this project. So yeah, definitely we'll develop this thing. Okay, do you have any doubts? Meanwhile, everyone, if you don't have UVM knowledge, okay, try to practice the UVM codes. Try to debug the UVM code. Okay, so then you will get the good understanding on how to debug this. Okay. Is it clear?
Yes, okay.
Yeah. Okay. So remaining Abhishek, Divyani.
Yes, ma'am.
Okay.
No, ma'am.
Yeah. Hello.
Yeah, ma'am.
So everyone understood up to here?
Yes, ma'am.
Okay, so we will start from this week only. Okay, from Thursday or Friday or Saturday. Okay, mostly Friday.
Yeah, ma'am.
Okay. Okay, if
Yeah,
you
ma'am.
have any doubts, please let me know. Rohit and Pankaj, everyone. Okay.
Yes, ma'am.
As
Okay.
of now, nothing, Prashanti.
Yeah, okay. So this is the main intention of these 3 months course. If you take much time to develop to understand the things, maybe we can't do anything. But try to put some more time, try to give some time for implementing this project, because nowadays in every interview, if you see any job description, especially from ARM, in every job description of ARM, they will mention this RISC-V processor, the computer architecture, basic computer architecture. These things they will mention. Okay, so it would be helpful for even freshers or experienced people. Okay. Okay, then thank you, everyone. We'll see in the next session.
Thank you, ma'am.
Ma'am, thank you, ma'am.
Yeah, thank you.
Thank you.
Thank you.
Thank you, ma'am.